So our next speaker is online. It's Khalil Damak, and the topic or the title of the presentation is Debiased Explainable Pairwise Ranking from Implicit Feedback. The online floor is yours.
Thank you so much. Hi, everyone. Can you hear me well? All right,
Yes.
I'll get started. So hi, everyone. My name is Khalil Damak. I'm a PhD student in computer science at University of Louisville. And today I'm going to present our paper entitled Debiased Explainable Pairwise Ranking from Implicit Feedback, which I co-authored with Sami, Khenissi, and Dr. Olfa Nasraoui. Recent research has emphasized the advantages of pairwise ranking in recommendation, and in this paper, we focus on the state-of-the-art pairwise ranking gloss, Bayesian Personalized Ranking, and aim to address two of its limitations, namely the lack of explainability and exposure bias. The BPR loss presented as follows aims to rank a positive interaction higher than a negative interaction for a given user. And here the state of interaction can be represented by the interaction random variable y, and the preference of the user towards an item over another item can be represented by the preference model f with parameters omega. The first limitation of BPR is the lack of explainability, and explainability is important because it allows the user to make more informed decisions. For example, if this user received the movie recommendation The Godfather, and they didn't know anything about it, they might think, why was this movie recommended? Or why should I watch it? However, if this same recommendation were accompanied with the explanation because you also liked Scarface, then they will have more context and more information based on which they will make the decision of whether to watch or not watch the movie. The second limitation of BPR is exposure bias, and exposure bias stems from the assumption that non-exposed items are irrelevant. More technically, as we said earlier, the BPR loss learns to rank interacted items higher than non-interacted items. However, what we ideally wanted to learn is to rank relevant items higher than less relevant items. And this discrepancy between interaction and relevance is what causes the BPR loss to be biased. And this result was already proven in previous related work, notably by Saito et al. However, what we're going to see in this paper is that when introducing neighborhood-based explainability into BPR, we introduce some additional exposure bias. And hence, we need to solve both explainability and exposure bias together. In this paper, we achieved the following four contributions. First, we propose an explainable loss function based on BPR, along with a matrix factorization model called Explainable BPR or EBPR. Second, we conduct a theoretical study of the additional exposure bias coming from the neighborhood-based explanations and propose an IPS-based estimator that is unbiased for the ideal EBPR loss. And finally, we perform an empirical study on 3 data sets to assess both the effectiveness and limitations of our proposed models. Given a measure of explainability, EUI, that tells how much item I is explainable to user U, we propose the following explainable BPR or EBPR loss. Here we weight the loss of every training instance U I plus I minus by the following explainability weighting term that regulates the importance of that training instance. For example, the higher the explainability of the positive item and the lower the explainability of the negative item, then the higher the explainability weighting term, and hence the higher the contribution of the training instance. This should lead the model to learn to rank both relevant and explainable items on the top of the recommendation list for an item, for a user, sorry. In this paper, we propose to use item-based neighborhood explainability, where EUI is equal to the probability of the user interacting with neighborhood items. However, this measure of explainability still relies on the interaction random variable. However, what we ideally wanted to rely on is the relevance. And again, there is discrepancy between interaction and relevance that would lead us to think that there could potentially be an additional exposure bias coming from the explainability. And to justify our claims, we first start by formulating the ideal EBPR loss, where we replace the interaction random variables by the relevance levels and replaced the explainability measures by the ideal explainabilities. Moreover, we proposed the following partially unbiased EBPR loss, or PU EBPR loss, where we used inverse propensity scoring to eliminate the original BPR bias and only focus on the exposure bias coming from the explainability. So the discrepancy between these two losses resides in the explainability weighting term, and which allowed us to theoretically prove that there is an additional non-zero exposure bias coming from the explainability. Finally, to eliminate this bias, we propose the following unbiased EBPR estimator, or UEBPR estimator, where we first used IPS to eliminate the original BPR bias, and also used a similar approach by dividing the explainability values by what we call neighborhood propensities to eliminate the bias coming from the explainability. And here we define the neighborhood propensity of a user towards an item as the probability or propensity of exposure of the user towards neighborhood items. Finally, we were able to theoretically prove that this UEBPR estimator is unbiased for the ideal EBPR loss. We performed experiments on 3 data sets, the MovieLens 100K, Yahoo R3, and LastFM2K. In our implementation, we estimated the propensity by the relative item popularity following previous work, and estimated the neighborhood propensities by the average of the estimated propensities over the neighborhood. In the first experiment, we aim to assess the overall ranking and explainability performance of the different approaches. First thing to note is that the explainable models presented the best results in terms of explainability overall. Also, EBPR presented the best ranking performance in the first 2 datasets, however, not on the LastFM2K dataset, and we're going to see later that this is related to vanishing gradients problem. Finally, the exposure debiasing seems to be hindering the ranking performance. However, even though we eliminated the bias in the training, the evaluation is still biased. And so to truly assess the impact of the debiasing on the relevance modeling, we perform experiments on the unbiased test set from the Yahoo R3 dataset, where a subset of users were presented 10 random songs to rate, which ensures that there is no exposure bias there. And hence, evaluating the model on this test set in terms of ranking evaluation is equivalent to evaluating it in terms of relevance modeling. Here we show the results in terms of ranking evaluation, and the explainable and unbiased models were the best performers in terms of relevance modeling, which means that the exposure debiasing actually works. In this third experiment, we aim to assess the impact of the data sparsity on the learning, and we do so by assessing the evolution of the average explainability values EUI with respect to the data sparsity. First thing to note is that the average explainability on the LastFM2K is at least 1 order of magnitude lower than the average explainability on the other 2 data sets in green and in red. And given that these explainability values are multiplicative factors in the update equations, then we can conclude that this will certainly lead to a vanishing gradients problem. Also, there is seemingly a linear relationship between the average explainability and the data sparsity, and hence the data sparsity directly impacts the vanishing gradients problem. In this fourth experiment, we aim to assess the impact of the neighborhood size on the performance. And the key thing to note is that after tuning the neighborhood size, the explainable models outperformed their non-explainable counterparts. And hence, the explainability seems to be improving the ranking performance or ranking accuracy with no trade-off. Finally, in this fifth experiment, we assess the popularity debiasing capabilities of all of the approaches. First thing to note is that mitigating exposure bias seems to also be mitigating popularity bias. So there is potentially a causal relationship between these 2 biases. And finally, EBPR outperformed BPR in all of the settings. And so there's potentially an inherent popularity debiasing embedded within the explainability. To conclude, we proposed a novel explainable pairwise ranking loss with a corresponding MF-based model called Explainable Bayesian Personalized Ranking, or EBPR. We theoretically quantified the additional exposure bias coming from the explainability. and proposed an IPS-based unbiased estimator for the ideal loss. We called it EBPR. And finally, we conducted an extensive experimental evaluation process that demonstrated both the advantages and limitations of our proposed approaches. These are the references that we used in this presentation. Thank you for your attention, and I'll be glad to answer your questions.
Thank you for your presentation. As always, you can ask questions by going to the microphone or using Slido. And we already have something online. Vasiliev Alexei asked, why did you not test it on data sets bigger than the movie lens 100K?
All right, that's a very good question. Given our computational resources, we have the choice of either increasing the number of data sets to cover more recommendation tasks, or increase the size of the data sets. So we chose the former. So it's completely due to the computational limited computational power that we had.
Okay, thank you. Well, more questions flowing in. So one question by Masaya Sato. How strong is the additional exposure bias by neighborhood-based explanation compared with the conventional exposure bias? For example, did you compare distribution of each propensity?
Oh, I see. So the question is about comparison between the exposure bias coming from the original exposure bias from BPR and the additional exposure bias coming from the explainability. That's a very good point. We did not do a comparison between the power or the strength of these two biases, but we'll probably do that in future work.
Okay, maybe you can read a paper about that next year on RecSys.
Hopefully.
Okay, one more question that I take from here is Sarababi says, thank you for the talk. How are the negative items sampled or disappeared? And did you compare the performance on rare items?
All right, so the negative sampling is performed. We did a random negative sampling in the training and in the evaluation. In the training, we sampled one negative item per positive interaction. We followed the same methodology that was used in the original BPR paper. And in the evaluation, we sampled 100 negatives for every positive test interaction because we used the leave one out evaluation process. But yes, well, we did not try, for the second question, we did not try any popularity-based sampling, for example, to account for hard negative samples.
Okay, thank you. I suggest going to Slido because there are lots of questions. So
sure.
I think we'll have some topics to discuss. Let's thank again. Khalil, thank you. And we move to our next speaker, who